Okay, we can make more questions based on electric flux. Say for an example, suppose this is an xy plane, and let's say the electric field is along the x-axis. Again, my consideration is parallel x-axis. Okay, parallel electric field lines means uniform electric field. Now suppose here, I consider a cylinder. Okay, I consider here a cylinder. I hope you can see it. So it looks so bad. Of uniform cross-sectional area. Okay, okay, all right. Now can we find the flux through it? Yes, can we find the flux through it? Let me make it properly. Okay. All right. So what would be the flux through the cylinder? What would be the flux through the cylinder? Okay. Now it comprises of two areas. One is what? The gap area. The gap area, what is the direction of the area vector? In the gap area, the direction of the area vector is given by this, right? Here at this gap, what is the direction of the area vector? Outward, right? And on the lateral side, what is the direction of the area vector? This is the one, right? Here also, what is the direction of area vector? This is the one. Then the flux through the cylinder will be what, student? Now see, area vectors are different on the lateral side and on the caps, right? The caps, how many caps are there? Two caps, right? Okay, then 2, I can write E dot A. This is for the what? This is for the, sorry, this is for the caps. And another is what? E dot whole lateral. This is the lateral surface area. Okay, then what is the direction? This is 2EA dot, what is the angle on the caps? This is 0 degree, while this is what? What is the angle between the electric field? Electric field is directed x-axis, so what is the angle? 90 degree. So this is 90 degree, right? So what it is? 2EA, right? So we have learned how to find the flux. Okay, now if we are clear about the electric flux, then we can go to the Gauss law. Okay, Gauss theorem. Okay, now let us come to the Gauss theorem, which is the name of the chapter itself. Gauss theorem. Okay, Gauss law, Gauss theorem. What it says? Okay, it says the flux, okay, it says the flux through the closed surface. See, some text for the closed surface they write this way. It means the same. Phi means the flux. Okay, so no need to bother much about it. It says the flux through the closed surface is equal to, suppose, let's say this is a sphere, closed surface. Okay, all right, and this closed surface, let's say, is having the charge E inside. Okay, fine. The closed surface is having the charge of Q inside. Then this Q will create the field in its surrounding, right? Then the Gauss theorem says that the flux through the surface, okay, is equal to the charge per unit epsilon naught. Okay, means previously this charge will create the field in its vicinity, right or not? Right? Fine or not? Now this will have the electric field, and how much is that flux. This is equal to, this is simply as that of what, same, don't bother if I write this way also. This is what it is, E dot A, and this is equal to what, the total charge enclosed by it per unit epsilon. Okay, so the flux, what is the easiest way to find the flux? Rather of going through this E dot A, where individually we were finding what is E and A angle, instead of that, if we directly go to the charge enclosed, divide by epsilon, then what we will get? We'll get the flux. Okay, this is the goodness of the Gauss theorem. Okay, so what it says, the flux through the closed surface is equal to the charge enclosed per unit what, per unit epsilon naught. Okay, you can see the notes for better idea of it. Okay, now I'll take various surfaces. Okay, now the previous one we had done some examples also. Suppose here is a cube. Okay, here is a cube, here is a cube, and let's say this cube is enclosing q charge. Okay, fine. Now no information about the electric field and area have been given so far. Then what would be the flux? The flux is, if the charge enclosed is given, what is the flux? So easy, yes or no, right? Similarly, suppose here is a cylinder, and inside the cylinder, let's say there are two charges, q1 and q2. Okay, then what is the total flux through the cylinder? Okay, the total flux is equal to how much charge it encloses. How much charge it encloses? Here in this case, the charge enclosed is q1 plus q2 divided by epsilon. Okay, so the flux through any surface is equal to the total charge it enclosed divided by epsilon. Is it clear? That is about the Gauss theorem. Now say, suppose I'm just saying, suppose here is a surface. Okay, all right, and in this surface there are two charges. Okay, one is plus q and another is minus q. Then what would be the flux? That means if the flux is given in terms of charges, okay, what would be the flux? The total flux, total charge is what? Plus q minus q divided by epsilon naught. So how much is the flux? It's 0, right? So we can know if the charge is given, and if the flux is asked, then we can even directly go to the, we can directly use the Gauss theorem and we can find the flux through it. Okay, is it clear? Then suppose here are two surfaces. Let's say this is having charge q and there is another surface q. What is the flux? Let's say this is surface 1, this is surface 2. What is the flux through 1? Q by E. Does it depend on the surface? Now flux through it, what it is? This is also Q by epsilon. So what information does it gives? Flux do not depend upon the surface shape, but the flux depends on what? The charge enclosed. Okay, in this case, though there was charge, but what is the total charge? It is 0. So what is the flux? It is 0. Okay, so this is the importance of the Gauss theorem. Okay, now there is one more thing. Suppose here is charge and here is, let's say here is one surface and here is another surface, 1 and 2. Okay, now what it be the flux through the surface 1? It would be what? Charge enclosed is what? Q by epsilon, right? Through surface 2, what is the charge enclosed? Still same or not? So is the flux depends on the surface? Small surface also same flux, big surface also same flux. Means what? Flux, what is that? It is independent, right? Independent of what? It is independent of the surface. So whenever the flux is asked and if the charge is given, then immediately we can find out the the flux without knowing the electric field, without knowing its area. Okay, this is the goodness of Gauss theorem. Okay, now this property of Gauss theorem, this particular thing about the Gauss theorem has made the finding of electric field very easy. Okay, like say for an example, we know that the flux, okay, flux is equal to E dot E, and that in terms of charge, what it is? Charge enclosed. See, this Q is the charge enclosed. Okay, say for an example, here is one surface Q, surface 1, and here is another surface, let's say 2. Okay, and here it carries another Q1. Okay, then what is the flux through 2? How much charge is enclosed by 2? Charge enclosed by 2 is Q1 and Q, right? So the charge enclosed term is very important, right? So while for 1 is what? It is Q by epsilon naught, right or not? I hope we are clear with it, right? Okay, then this one, if I write in general, like sometimes the electric field may not be uniform, then what it can be? It can be written as E dot ds or dA. The textbook will, it depends upon the textbook. Okay, now as the closed surface we are talking, so here this round, okay, on the snake, the round, snake means integration, the round means closed surface. This is equal to this. Now one thing, okay, if we know the charge, all right, if we know the area, then finding the electric field becomes very easy. Okay, so Gauss theorem has Gauss theorem is widely used, okay, for finding electric field. So E finding, okay, is one of the application of Gauss theorem. E finding is applied, okay, in what to say, in Gauss theorem. Okay, E finding is applied in Gauss theorem. Okay, so one of the application of Gauss theorem is to find the electric field very easily. Okay, electric, for this one particularly we use it. Okay, now in order to use a Gauss theorem, right, we need to have a closed surface, right? Then for that purpose, what we do, like suppose suppose here is a line, okay, on the line there is uniformly distributed charges, right or not? Okay, let's say this type we call it as line charge. Okay, this is line charge. Okay, uniformly distributed charges are there. Say here you need to find the electric field. Okay, now what you are going to do, so far we know that electric field due to a point charge is equal to what? 1 by 4 pi epsilon q by r square for a point charge only. Now for this point, electric field here you have to find for this point, electric field you have to find for this point, you have to find electric field here, this point, electric field this point. Lots of mathematics will come, very very difficult one to do. Okay, but instead of that, if we use the Gauss theorem, then easily we can compute the electric field at this point. Okay, then some idea we are going to use that one. Okay, let's see it. Like see, to apply Gauss theorem, okay, depending upon the necessity, to apply the Gauss theorem, we make something depending upon the necessity, which is known as a Gaussian surface. Okay, I'll give example, then I hope you will be able to understand it. Okay, Gaussian surface, and this making of the Gaussian surface, it depends upon symmetry. Okay, symmetry, I hope the spelling is correct. Okay, like suppose I'll stick with this one. Okay, line charge. Okay, now at this point, say you have to find out the electric field. Okay, now from this symmetry point of view, let's say this distance is r. Okay, and at this point we have to find the so-called electric field, which we don't know, but whatever the value of electric field here at the distance r will be, similarly at the same distance on the other side, the electric field here will also be the same. Yes or no? Why? Symmetry point of view, equidistance from the line, right? Yes or no? Then similarly, the distance r means what? The electric field at this distance r and at this distance r will be the same, right? Now if we joined this, I'm doing the construction. Okay, then let's say it is of uniform charge density. Okay, means what? Whatever the per unit length, the charge is the same. So what type of surface we get? We get a cylinder, right? So what if I want to use the Gauss theorem? For the Gauss theorem, closed body is needed, right? And to find out the electric field at this point, I have assumed the imaginary surface. In this case, it is a cylinder. That is the Gaussian surface. Okay, clear? Is it clear, student? I hope it will be clear. So Gaussian surface is what? It is imaginary, but how we are going to make it? We see the symmetry. All right. Okay, let's see. Here is a point charge. This one we have already done it. Okay. Now it is desired to find out electric field at this point. We have done this derivation already, but still. Okay. Okay, we know that E is equal to KQ by R square. Right? We have done it already. So now at this distance R, electric field is E. At the same distance R, the electric field will be the E. At the same distance R, electric field will be E. At the same distance R, electric field will be E. If we join these things, then what it will be in 3 dimension? It will be a sphere. So if I want to find out the electric field by the use of Gauss theorem, what type of Gaussian surface do I need to consider? The Gaussian surface have to be a sphere. So this is what? This is a Gaussian surface. Okay, this is a Gaussian surface. Okay, all right, clear. Okay, another, let me see. Here is a ball where the inside all the charges are there. Okay, now if I want to find out the electric field at this point, what type of Gaussian surface do I need to consider? Equidistance r, equidistance r, equidistance r, right? Then again, what type of surface it need to, it also have to be a sphere, right? So in this case, what would be the Gaussian surface? The Gaussian surface would be a sphere. All right. So Gaussian surface, I have given you there in the notes that Gaussian surface is the artificial imaginary surface in order to use the Gauss theorem. Okay, in order to use the Gauss theorem. So based on that, we are going to derive the expression of electric field due to so many types of charge distribution.